So let's just add a little bit extra to 5.2. Remember, we're talking about charged particles in a magnetic field. What about current in a wire? Current in a wire in a magnetic field. So imagine that I've got our magnetic field again, and I've got a wire going through there with a current in it. Now, that current is a whole lot of charge going through there. And we know from earlier that force is going to equal the charge times the velocity and such like. And if you sit down and actually work it out, for a wire in a magnetic field, the force is going to equal B I L sine theta, where B is going to get me the magnetic field again, and that's measured in Tesla. I is the current, and that's going to be measured in amperes. L is the length of wire in the magnetic field, and the field. So we're only going to count the bit of wire in the field. I mean, if it's short, we'll only count that much. If it's longer, then we're only going to count the bit that's actually in the field. And that's going to be measured in meters. And if you actually work this all, and sine is what angle the wire is. I mean, if the angle were going straight into the page, it would experience no force, because sine theta, theta is 0, you multiply anything by 0, vanish. But so we're going to end up with a force measured in Newton. So let's just do this quickly. This is called the motor effect. Basically, the motor effect says if you put electricity in, motor effect, and we'll be hammering this a lot, is basically electricity in and motion out. So if you put in electricity and it causes it to move, then it's the motor effect. We also get the generator effect, which is the exact opposite. And the generator effect, we stick motion in, and we get electricity out. So these two are opposite effects to each other. So this is the motor effect. We go and stick current through there, we put electricity in, creates a force, and if they can, it will move. So let's do an example. A 10 centimetre wire in a, 0.6 Tesla field. So we're going to be using neos. Has 5 amps put through it. What force? What is the force? Okay, so just separate that out. So what's the force? Well, so force is equal to BIL sine theta. We're going to assume that until a perpendicular 0.6. Whenever we're running motors, we always try and set these up perpendicular. So for the magnetic field is 0.6 Tesla, the current is 5 amps, L is 0.1 meters, sine 90 degrees, so it's at 0.33, 0.3 newtons. So the question is now, I mean, that's not a very powerful motor. How can we increase the size of the motor? Well, often when they ask you, how do you increase the size of something? Look at the equation. What I can do to increase the force is I can increase the magnetic field. I might use the electromagnet and run it up to a couple of Tesla. That will increase the size of that. Or I can increase the current. Instead of 5 amps, if I stick 10 amps through there, I'll get twice the force. Or I can increase the wire. And what actually happens in the case of a motor, instead of having one wire going through there, you have hundreds of wires going through there. You actually have them looped. coil. But anyway, so the big thing here is the motor effect. This is the motor effect, and also the whole current a charge going through a magnetic field. Motor effect, you put electricity in, you get motion out. Generator effect, you put motion in, you get electricity out. So, okay, so we'll carry on in a sec with section 5.3, electromagnetism.